About a note on Matsuda monoids.
Thank you, ma'am, for the introduction. And I would like to thank the organizer for giving me a great opportunity to speak here in the special occasion of celebrating Ramurthy sir birthday. Happy birthday, sir, and also celebrating his contributions to number theory. Uh, uh, so Ramurthy sir is my postdoc supervisor, and along with the Professor Brad Rogers. So thank you for the supervision, and also my PhD supervisor, ma'am, is also here. So in the morning, we had a great talk by Kumamurthy sir on Artin primitive root conjecture. I think Ramurthy sir's talk is also related to Artin primitive root conjecture. In this talk, we'll be relating Artin primitive root conjecture to problem about certain monoids that have been studied independently in algebra. And using these connections, we solve some problems related to the certain monoids. Let me begin with introducing few notations. N subscript 0 denote the set of natural numbers along with 0. Q0 plus denote the set of positive rationals including 0, and similarly R0 plus is defined, and MBA commutative, torsion-free, cancellative, additive monoid, and F denotes a field, and F of x comma m denote the set, ring of polynomials with coefficients in F and exponents in M. For example, if you take m is equal to n0, F of x comma m is nothing but F of x. Okay. The question which we are interested in is, when does the polynomial x power alpha minus 1 is irreducible in f of x comma m for a non-zero element alpha in M? Maybe I'll introduce the following definition, which will be helpful later. A non-zero element in alpha in M is said to be indivisible if it cannot be written as n into x for some natural number n greater than or equal to 2 and x in M. For example, if you consider the monoids Q0 plus and R0 plus, there are no indivisible elements. In N0, the only indivisible element is 1. And if you exclude 1 from that monoid, the N0s removing 1, the indivisible elements are exactly is equal to the primes. Okay. So suppose alpha is divisible, say alpha can be written as n into beta with n greater than or equal to 2, then x power alpha minus 1 it factorizes in f of x comma m as x power beta minus 1, 1 plus x power beta plus x power 2 beta plus so on up to x power n minus 1 beta. So if alpha is divisible, x power alpha minus 1 is it's reducible. So hence, if x power alpha minus 1 is irreducible in f of x comma m, then alpha must be an indivisible element in M. So the natural question is, suppose x power alpha minus, natural question is whether the converse is true. That is, if alpha is an indivisible element in M, then whether the polynomial x power alpha minus 1 is irreducible in f of x comma m. Okay, and we say that M is a Matsuda monoid if the converse is true for any field F. For example, R0 plus, Q0 plus, and N0 are Matsuda monoid. In fact, in 1975, Matsuda proved that any torsion-free abelian group is a Matsuda monoid. So this will give a large class of Matsuda monoids. Before moving further, going to the next slide, let me introduce the following definition. We say that M is a Matsuda monoid of type 0 if the converse is true for any field of characteristic 0, and same definition for Matsuda monoid of type L. In 2018, Christensen, Gibson, and Kolosman proved that the monoid N0 excluding 1 is not a Matsuda monoid of type 2 and type 3. They proved by this finding explicitly indivisible elements in M such that x power alpha minus 1 is actually reducible. For example, 7 and 11 are indivisible element in M, but x power 7 minus 1 is reducible in f2 of x comma m. Here is a factorization, and x power 11 minus 1 is reducible in f3 of x comma m. Here is the factorization shown on the slides. And also they also raise the following question: whether there is a prime L for which M is a Matsuda monoid of type L. Okay. So therefore, this question is related to the non-emptiness of certain subset of primes. Let L be a fixed prime, and let E of L denote the set of primes P for which x power P minus 1 is reducible in FL of x comma M. The result of Christensen, Gibson, and Kolosman states that E of 2 is non-empty and also E of 3 is non-empty. And in fact, 7 belongs to E of 2 and 11 belongs to E of 3. So going one step further, we can ask whether there exist infinitely many primes in E of 2 and E of 3, whether they are of positive density, and what can you say about E of L for primes L greater than 3. Okay. And these questions were answered by Dylada, but under the assumption of generalized Riemann hypothesis for Dedekind zeta functions. Assuming generalized Riemann hypothesis for Dedekind zeta function, they show that the set E of L has positive lower density. In a recent work, we remove the assumption of generalized Riemann hypothesis in the above result. We show that for any prime L, the set E of L of primes P for which x power P minus 1 is reducible in FL of x comma m has positive lower density. In fact, E of L has lower density at least 1 minus product P greater than or equal to L 1 minus P into P minus 1. And of course, this infinite product reminds us of Artin's constant, which is related to Artin's primitive conjecture. We already have a nice talk. So I'll not go too much into the details about Artin's primitive conjecture. Let me quickly recall. And the story goes back to Gauss. He observed that if you consider the decimal expansion of 1 over 7, which is 0.142857, 142857, 142857, so it has period 5. And 1 over 11 has period 2. In fact, if you take any prime P, which is not equal to 2 and 3, the period of the decimal expansion is exactly equal to the smallest natural number k, for which 10 power k is congruent to 1 modulo P, which we call the order of 10 modulo P. In terms of the group theoretic language, the smallest such k is precisely the cardinality of the subgroup of Fv cross generated by 10. By well-known Lagrange's theorem, the period will be a divisor of P minus 1. Hence, the largest period possible is P minus 1, which is a case when 10 generates Fv cross. In that case, we say that 10 is a primitive root modulo P. So the next question is how often this happens? Okay. A precise conjecture was formulated by Artin in 1927. If A is an integer not equal to plus or minus 1 or a perfect square, then there exists infinitely many primes P for which A is a primitive root modulo phi. Moreover, if Na of x equal to the number of primes of 2x for which A is a primitive root modulo P, then there exists a constant A of A depending on A such that Na of x is asymptotic to A of A into x by log x as x tends to infinity. And in 1967, Houle proved Artin's conjecture as well as an asymptotic for the Na of x under the assumption of general Riemann hypothesis, where A of is a constant, summation d is equal to 1 to infinity, mu of d by nd, where mu is the Mobius function, and nd is the degree of the extension, which is the compositum of the fields q adjoint with e power 2 pi I by p and a power 1 by p. And the constant A of A is also can be written as an infinite product with delta as a correction factor. So this is under the general Riemann hypothesis. The first breakthrough is due to Gupta and Professor Ramurthy sir in 1984, and they proved that there exists a set of 13 numbers such that for at least one of the numbers in that set, Artin's primitive conjecture is true. And later, the size of this set was reduced to 7 by Gupta, Ramurthy sir, and Kumamurthy sir. Later, it was refined to 3 by Heath-Brown. Hence, as a consequence of these results, we have beautiful theorem that numbers among 2, 3, 5, Artin's primitive conjecture is true. Okay, let me go back to Houle's result. If you assume the general Riemann hypothesis for Dedekind zeta functions, the set of primes P for which A is a primitive root modulo P has density equal to A of A. In a recent result, we remove the assumption of general Riemann hypothesis in the upper bound for Houle's result. More precisely, we prove that if A is an integer, non-zero integer, not equal to plus or minus 1 or a perfect square, then the set of primes phi for which A is a primitive root modulo P has upper density at most A of A. And the method used is also applicable to a plethora of art-in type questions. Here are some of the references. Thank you. So I would like to also thank again for the organizers for giving me this opportunity, and also take this occasion to thank Professor Ramurthy sir for his excellent books from where we gain a lot of knowledge and insight into number theory. Thank you, sir. You are an inspiration.
Any questions? Yes.
Sorry, I can't hear. The A of A, delta of A into the product?
X to the 7th minus when you factorize it. Is it like, what are you doing like math mod 2? Is that where you get the
Asking about the factorization. If you factorizing to the factor x to the 7 minus 1
like the fourth slide?
Okay, x power 7 minus 1, x power 11 minus 1. They did by explicitly checking the each and everything, right? X power 7, degree 7. So we can by explicit computations.
So was it like you're doing all those multiplication mod
It's modulo 2 because the field is F2, the coefficients in F2, so it will be a modulo 2.
and then mod 3?
Or mod 3, yes, that's it.
Any more questions? Comments? If none, we will thank the speaker.
Thank you.
So we have 5 minutes. You have more emails to check? Yeah, he finished early. He still, his mode of speaking is quite different than rest of it. It's a typical, you can see the way he speaks. You should have mentioned what is Golan's conjecture. Two more talks to do and I'm done. One more is Michelle, last talk is Michelle's. Michelle's talk. Watch me. I should ask him. He, I think, will be doing so. Michelle? Michelle? You will be using slides, right? You have already given. Yeah. Okay. Okay. Maybe we can start out.